Okay, so hi and welcome to a session of video notes for my class, which is video notes 8.8 on exponential growth and decay. Now, we've seen growth and decay a little bit before, and we've definitely explored exponentials quite a bit. And you're like, well, why are we revisiting this? Well, growth and decay can be more intricate. They can have a few more details that we haven't explored. So we're going to take a little bit of time today and see if we can explore them just a little bit more. Now, exponential growth and decay are both exponential functions. You should be familiar with an exponential function. It should look something like this. Y equals a times b to the x or t or whatever happens to be, some various form of that, where b is your base, a is your initial value, and x is the number of periods, times, or events that occur. And we understand this to grow, well, exponentially, meaning that every time it increases, it either gets larger in that increase or significantly smaller in that increase. So it's not like a linear where it's a constant change. It doesn't increase the same amount. This one gets larger and larger and larger as it goes up, or smaller and smaller and smaller as it decreases. Okay. If it gets larger, we call that an exponential growth, and if it gets smaller, we call it an exponential decay. Again, stuff you're familiar with. However, what's new then is we're going to take a look at the b value. Really, that's where we're going to spend our time today, is what's different about b today. We've said b is a growth factor, meaning how much larger it's getting, or if it's a decay, how much smaller it's getting based off of that b. But we can talk about that in terms of what we like to call percent. So if we take a look at the b here, you'll notice that b inside the parentheses, usually correct, looks a little bit different comparatively if you look at the exponential and the growth. So let's start with the exponential growth here and take a look at what this really is. Okay, we're going to break b up so that we can look at it as the percent of its increase. Okay, and to be able to look at it, the percent of its increase, we're growing from whatever we started with. So if it's growing by 3% each time, you're going to take 100% of what it was and you're going to make it 3% bigger. So the next time you see it, it's 103%, right? If you were talking about taxes, a tax on a candy bar at the store that was $1, the candy bar costs $1, but tax adds a percent to it. So it's $1.06 or 6% bigger. That's what we're really looking at today with exponential growth and decay, is their percent factor. If they're growing by some percentage, not 100%, like 200% larger, that's easier to do. At 300% larger, that's easy to do because it's a 2 or a 3 for the B. But if it's a percent, like the candy bar tax, it's 6%. How do you make it that much bigger? Well, you got to look at it as in two parts. One is that percent increase, right? And that's what this R is. So R represents whatever the percent of increase actually happens to be. In the exponential case, it's the rate of decrease or the percent decrease of it. The one here, which sometimes confuses people, represents what it was, 100% of whatever the original amount was. And so that's how I like to write this. This represents 100% of what it used to be, and then we're adding on for a growth, or we're subtracting for a decay from that 100%. So if we're adding on, it's a little bit bigger than what it used to be. If we're in a decay, it's a little bit smaller because we're subtracting, right? It's a little bit smaller, which gives us a general form here that we can kind of talk about. If it's an exponential growth, your b value will be greater than 1. Some value greater than 1. It can be a decimal, it can be a fraction, it can be an integer. It has to be greater than 1, though, larger than 1, including 1. It can be 1. It's not a very exciting growth. It's really no growth. It's the 100% just stays the same. So really, it's got to be greater than 1. If we look at the exponential decay, in contrast, it's got to be a value between 0 and 1, not a negative value, which maybe you thought, you're like, oh, if growth is larger than 1, then exponential decay has to be less than 1 or negative values. And it doesn't actually. It doesn't include any negative values. It has to be a decimal, and that's how we put this interval here. It's got to be between 0 and it's got to be between 1, meaning some point, 0 point something. I don't care what it is, but it's got to have a 0 point to be a decay. Okay, the A value is what you would expect it to be. That's the initial amount. The R value then is that percent. That percent increased, sometimes referred to as an interest rate for both. It doesn't really matter what it happens to be. And T is your time or events or periods, whatever it happens to be normally. So those don't change in the way that you think about them. The only thing that's super new here is how to look at B as two parts. And really, the only part that super matters is the rate increase. The one is just you saying, oh, it used to be this, and we're adding on this piece or subtracting this piece in case of decay, right? So if you can get that part down, then you've kind of got the concept of it. So just remember, another thing to remember is exponential is a growth, which means your y values are increasing or getting larger, and your decay value are where your y values are getting smaller. So what does that look like? Let's put all this in perspective again. I know we've seen this before, but let's take a peek at it again just to kind of summarize these two next to each other since we're looking at them together. So you'll see that I have a couple of graphs on here. I've got two exponential growths and I've got two exponential decays sitting here in front of you. If you want to see the function, just to kind of map it out so you have a little better look, let's take a look at the growth here. I graphed the function, right, or made a table for and graphed the function of f of x equals initial value of 1, and its growth factor is 2. I didn't use a percent here because 2 is a little easier to work with to make points. So 2, so it's a 200%, or if you wanted to break that down, it's 1 plus another 100%, right? So it's growing by, it's doubling. It's not a percent like decimal increase. It's a whole nother one. So it's 1 plus 1. So you can see that R value and you can see the 100% of the original there. So we can calculate the table values for this pretty easily by plugging in values of x. So a negative 1 here, if we calculated that, we're going to get 1 times. And if your exponent is a negative, remember that means move positions or move it down. So in this case, we're using a little bit of our exponential properties. So we got 1 times 1/2 or equals 1/2, right? If we plug 0 in here, anything to the 0 power is 1. 1 times 1 is 1. I'm cheating here a little bit. I didn't write my work down. There it is. And then if we plug 1 in here, so it's going to be 1 times 2. And we're going to get 2, and if we plug 2 in there, 2 squared is 4, so 1 times 4, which is 4. And again, the notes aren't about this. I just wanted you to see where I got these table values. So this would represent an exponential growth, right? It's getting larger. If we look at it, it's getting 100% larger each time. It's doubling, right? Its percent increase is 100%. I know that's a funny one to start with. We'll take a look at some other examples. Actually, let's do that now. If we look down here, here's some other examples of what an exponential growth may look like. Again, focusing on the B value. This one would be growing by 200%, or it's getting 300% larger each time, right? Where are the R values here? Well, it would be 1 plus 200% growth. You can see it there. If you look at the next one, again, notice your B value. It's larger than 1. It's a decimal larger, it's 0.175 larger, but it is larger. And let's look at this one. This one is 2.34, so it's 1.34 larger. What are the R values of these? What percent are they growing by? Well, this one's growing by the percent of 1 plus 1, or 0.175. Sorry, I can't spit that out, right? This one's growing by 1, that's the 100% of the original, plus its growth factor, it's increasing by 1.34. So you can kind of see the percent increase. This is what it's increasing by between each x value. That's how much larger the y value is getting. Okay, so what does that look like? Well, that looks like over here, as I'm going between these points that we calculated, this percent should be getting 100% larger or doubling. And so if I went up by 1, the next one looks like in y values, right? My y value increased by 1 unit. If I look at the next point between them, so going between these two, look at my increase. It doubled. And you can go back one more. We can take a look at the negative 1 value. It went up by 1/2, and the next value went up by 1. I'm sorry, I went right to here. We're looking at this value. It went up by another 1/2. So each time we're looking at it, it's increasing by that rate. So this here is, these increases are the percent increase, right? That's what we're looking at. That's getting larger by that. If you look at the next value, right, and we didn't do that in the table, but it's from 3. We went up 2 values for y between 1 and 2, but between 2 and 3, it goes up 4 values. So again, it doubled, and that's that percent increase. And you're like, well, Mr. Hallam, you forgot to talk about something with your exponential growth here. What about this one going down? Well, the one that's decreasing, we should have some familiarity with this, means that one new thing, actually we'll just keep the green, means that my a value is now negative. It's increasing in the negative direction. Remember, positive and negative are directions on a graph or a number line or wherever it happens to be. In this case, it means a negative y value, so we're going to get farther down or grow in the negative direction. And that's weird to say, but that's what's happening. It's growing in the negative direction. How's another way to look at this? Well, remember we've talked about the asymptote, the line at which the function gets infinitely close or infinitely far in this situation, right? This is a growth, so it's getting larger and larger, infinitely larger away from this line. If it's a growth, it will be growing away from the asymptote. Okay. In contrast, let's look at our exponential decay. Our exponential decay should do from the asymptote. Here's our asymptote again, right? There it is. It should be growing towards as we move. Again, we should probably write that down from left to right. We always work in that fashion. So from left to right, we should be getting closer and closer and closer, infinitely close, but never touching that asymptote. And that represents a decay visually. Well, let's run the numbers real quick just so we can say that we did it. Here's our function that I used for here, all right, at least for the top half. Here's this function, this exponential decay, which I used 1, and the growth factor is 1/2 x. So if we wanted to look at the 100% of the original minus 1/2 or 0.5, whatever you want. Oops, I can't write 0.5 or 1/2. That's what's happening there. That's where that growth factor came from, 100% of the original, and then we're cutting it in half. Okay, again, I use this one for easy calculations. So if we wanted to go ahead and quick calculate these points so you could see where they came from, if I put a -3 here, remember that tells me to move the positions, right? So I'm going to go ahead and switch those, which would give me 1/2, right? And then it's cubed. Don't forget I forgot to cube it there because it was a -3 going in. So it's 1/2 cubed, and that's going to equal 8. So that's why when we put in -3 here, right, it goes up to 8. And then this one's going to go down to 1/2 squared, because again, that negative's flipping this 1/2, and we're going to get 4. And then I'm going to put in -1, and I'm going to get 1/2 or 2, and then I'm going to put in 0, and that's going to give me 1 to the anything in to the 0 power is 1. I'm going to get 1, and then if I put in 1 in there, I'm going to get 1/1/2 or 1/2, and I could keep that going, but that's where these values came from. And again, if we wanted to do and this is a positive exponential decay, right? Positive exponential decay there. And if we wanted to look at the negative exponential decay, meaning from left to right, it's getting closer and closer. They're always getting towards that asymptote for decays, right? If I wanted to do the negative direction, that means that this a value would be a negative here, and all of these values would become negative, is what essentially would happen there. Right? And so again, does that matter? No, that's things that you can calculate. These are skills that you possess. I just wanted to show you where these functions came from. So what are some other exponential functions or exponential decays look like? Well, let's start looking at all of their b values, because that's really what matters here. And notice each one of their b value is a decimal of some sort. And that's the most important thing to notice about an exponential decay. It doesn't matter that the a value, what it is, that's 7, that's fine. You're like, wait, but that's a third. Does that mean something? No, it just means that your a value starts at 1/3. And this a value starts at 14.5. So if you look at these should all be some form of a decimal. All right, so what we're going to do next is I'm going to do some examples, some real-life examples showing you how to interpret exponential growth and interpret exponential decay and calculate with them. Okay, thanks for watching. Make sure you check out the next video. We'll see you there.